where you can get Cedar, right? So it's the same as with Cosivina, as Gregor showed you already. It's right under Learning DFT and then Software. And then you can click here on the Setup Cedar button, and there you get onto the Cedar homepage, cedar.ini.rub.de. And under this only button on the page, you get immediately to the download section here. And we recently have, or not recently, maybe 2 or 3 years now, we have these portable versions that are already pre-compiled. And in a last-minute effort, we pre-compiled also new versions for each of the 3 major operating systems here. And the idea is that you can just download these, unpack them, and immediately run them. And this will get you sort of our latest portable version. But if you're really interested into writing code for Cedar yourself, which you probably won't need to do, then you could go here under source code, where our GitHub is actually, and you can then compile everything yourself. But for that, you need a lot of libraries, and it's usually a bit of a hassle to set that up. So if you're interested in that, we have some tutorials on that, installing and running Cedar. But also don't hesitate to contact us. We can usually speed that up by a lot because we know a lot of information there. But for this week and also for today's exercise, it's totally enough to download just the appropriate version here for your operating system. And what you will get then is you will get sort of an archive, a folder here that contains at least a run Cedar but on Windows, and I think an app under Linux and Mac. And if you double click on it, it will start the Cedar software. And let me move your faces away because then I can show you everything properly. So the idea of Cedar is that instead of writing code like Gregor just showed, instead of writing which fields are in the architecture, you can really graphically assemble everything. So you can drag and drop certain elements onto into the architecture. And for that, Cedar has 3 major areas. And the first one on top here is sort of your toolbox, where you can find different steps here. And the most important step here, of course, is always the neural field. That's the one you're going to need the most. And the idea is that here below is the canvas where your architecture is, that you can drag and drop by clicking on the neural field and dragging it here onto the canvas, create such a neural field. And the last major point of Cedar is if you click onto an element here in the canvas, on the right-hand side, you will see all the parameters of this element that you clicked on. And the first thing I want to do in order to familiarize you with that is I want to reconstruct the simulator that you saw yesterday with the 1D field and the Gaussian inputs, so that you know what we're doing here. So that was a 1-dimensional field, right? And the default in Cedar is already 2-dimensional. So you can see here the dimensionality parameter. So the first thing we need to do here is to change this to 1. And you also see here that this icon will change. And what is graphical about all this is that every element here in Cedar, you can right-click and then plot. So what you can do here, for example, with the field is you can click on field plot, and then you see this hopefully familiar plot from yesterday. And if it's not familiar, you can right-click here and click on legend. And then you see that you have 3 things plotted here. On the one hand, the input sum, then the activation, and in the end, the sigmoided activation. And right now it's just straight lines. That's because there's no simulation running, right? So in order to start your simulation, there's a big play button here in the top left. And if I click play here, you should see some wiggling here in the bottom. So you see that there's some neural activation, and you just see noise right now. And what you had yesterday, of course, was you had the ability to add inputs to this neural field. And in Cedar, it's not that your interface is fixed, but that you can assemble it on the fly. So the idea is here that you can, for example, take a Gauss input from your toolbox, drag it in, and then it is possible in Cedar to connect steps with one another. And the idea is always that on the right-hand side, you have output slots, and on the left-hand side, you have these input slots. And the idea would be now to connect this Gaussian input to the neural field. Problem is now, if you want to do this, you see that this is red here. This is because the Gaussian is also of dimensionality 2, and we need to decrease this to 1. That's sort of a general rule in Cedar. If you want to connect 2 elements, they need to have the same dimensionality and the same size. And the size is basically the sampling of the the neural field here, for example. So of course, we assume that this is sort of a continuous space, but on a computer, you cannot sort of define an infinitely large space. So we just say, okay, we have here 50 positions that we sample from in the neural field. And we do the same for the Gaussian input. And if we now connect this by just dragging, left-clicking here, dragging to the input here, you will see that now a Gaussian input emerged here. And similar to the neural field, if you click on the Gaussian input, and I already used this, you have here the parameters of the Gaussian, and that is dimensionality and size. These are pretty fixed. But then, of course, there's the amplitude. So how big is this Gaussian? There's the center, or the mean value, if you want to call it. So it's also in this range between 0 and 50. And then there's the sigma, so the width of the Gaussian that you can modify. And you can, of course, because it's its own element, also plot this Gaussian here by right-clicking and plot all. And then you see basically only the Gauss input here in isolated form. And if I modify this, you see also the modification happening here in the Gaussian input. So what you can now do, of course, very easily is add a second input to the neural field. And for that, you just, again, drag the Gaussian input into here, change its dimensionality to 1. And then you can also click on it and drag it over here. And now you see two inputs here to this neural field. Maybe to show you the overview, also plot Gaussian input number 2. And what you see here, what's probably a bit hidden, is you can drag and drop every plot here. If you click right around the name, there's no visual guiding for this, and you can also expand the size all on the fly. So just that you can see that. And what I want to do now is I want to show you now how you can sort of reproduce yesterday's simulation. And for that, you need to manipulate the field parameters. And these are now not sliders, but numbers, but you can find them here on the right-hand side. So from top to bottom, I will go through each of these parameters. So the first two are dimensionality and size, and they are also grayed out here because while the simulation is running, you cannot change them because that would crash the simulation. So the first parameter that we have here is the time scale that you maybe modified yesterday already. That is sort of the multiplication in front of the field equation, the tau, that then sort of makes sure how fast the field changes with each time step, or like a field with a huge time scale changes slower, while a field with a small time scale changes faster. But the more important one would be the resting level that defaults here at -5. So if you change that, for example, you can raise everything up here, because then now we would have a resting level of -2. And the next parameter would be the noise gain. You can, of course, have 0 noise, and you don't see any movement here. If you ramp that up, you can have a really noisy field. Usually, you want to have some noise, but not that extreme that you cannot sort of guarantee any behavior in your field anymore. The next thing looks a bit more complicated, is the sigmoid function of the field that you can change according to your liking. The default in Cedar is this absolute sigmoid, which is just a faster version of the regular sigmoid, but you could also change to this exponential sigmoid, for example. But let's just leave it at the default value here. And what you can change about that would also be the beta. That might be interesting. So right now we have a very high beta. That means our sigmoid, so the red line here is the sigmoid activation, is very steep, right? It's almost a square that you can see here above threshold. If you want to verify that, you can verify the beta here, let's say 10, and it gets a bit smoother. Maybe if you choose 1, it's really smooth. But the default is very high because that makes it very easy to distinguish between having a peak or having no peak there. Then a parameter that you also learned yesterday is global inhibition here. With that, you can make sure how much inhibition a peak that is in the field is already, how a peak in the field inhibits all other locations in the field. And I think in the Cosivina plots or in the simulator that we have on the webpage, you can also see this. So in Cedar, you can do this by going under advanced plotting, and then you get multiple things you can plot, for example, the input, the output, activation, only the noise. But the thing that we're interested in right now would be the full lateral kernel. And then it also gives you multiple options to plot, but in all honesty, the best one is usually the mat data plot, and just always click on the thing that's highlighted in bold here. So right now we would have this lateral kernel, and that has some global inhibition. So maybe to show this, if we increase this, global inhibition here is now at minus 0.25. So this is where you can play around with that. And the other thing would be our excitatory kernel here. That is what you see right below. Under lateral kernels, there's sort of a list of different kernels that work here. So right now we have a Gaussian kernel that has an amplitude of 1 and a sigma of 3. So if you change the amplitude again, you would change here the amplitude of the lateral kernel. Or if you change the sigma, you would change the width by either being super small or super wide. And one thing that I want to show here already is that having one Gaussian is of course not enough to sort of have all kernels that we use in dynamic field theory. And the most important kernel that we actually use in a lot of times is the so-called Mexican head kernel, where you have no inhibition globally, but you have some local inhibition, and then in the middle you have a lot of excitation, where the Mexican head comes from. And there is no predefined Mexican head kernel in Cedar, but similar to the architecture, you can construct it yourself. So the idea is here that you build such a Mexican head kernel by using two Gaussians, one excitatory, that's small, and one inhibitory, that's wide. And we do this by clicking here on Gauss kernel and then a plus. And this way we have now two Gaussian kernels. One has an amplitude of 1.9 and a sigma of 3, and the other one has an amplitude of 1 and a sigma of 3. So both are excitatory. And we want to create now our Mexican head, make one of those inhibitory and make it a bit wider, let's say something like 10. Maybe decrease the amplitude to -2. And if we increase now the excitatory part, get sort of this nice Mexican head shape, right? Where anything that's now above threshold excites itself, but also inhibits these nearby locations. I think you had this in the lecture. And this would be sort of now the step from yesterday, where you have like two Gaussian inputs, and you can manipulate your lateral kernel by setting the global inhibition, setting the local excitation and the local inhibition. And this way you can then form peaks or play around with that, play around with the inputs by removing them, adding them, or changing their values. That was now a lot of overhead to create the simulator from yesterday, but I hope you can see from this sort of the benefit this has, because you can now structure a whole field architecture by adding multiple fields, adding multiple inputs, and so on. So what Cedar allows you to do, especially because the default parameters are all pretty neat, is to do a very fast prototyping. So what you will maybe also experience in the summer school is that you can get very fast, very far actually with the dynamic field architecture. And what I want to do now for the rest of this Cedar demo is I want to actually show you how to create 3 fields with 3 different regimes. And this is all based on what we have here under documents in our exercise 3 field architectures. So if we click on that, you will find here a PDF on the Cedar tutorial exercise. And it also explains where you can download Cedar if you didn't write down the URL or anything. And it also explains in very much detail what I'm going to do now in this demo. So you can see my demo now as an add-on to this text. If you're not into video descriptions, then maybe text alone might be enough to also recreate everything here. What I will do now is I will show you first a multi-peak field, then a working memory field, and in the last step, a selective field. And how you can do this is also explained here. And what this will then help you in the end to do this exercise number 4, where you will then have the homework to create your own dynamic field architecture based upon these 3 principles of working memory, selection, and multi-peak detection. And yeah, this is sort of where I'm going to start now by following through these explanations without reading them. So I will just explain what I'm going to do here. One thing that might also be quite important is whenever you want to keep your architecture around, you can of course save your architecture and then open it later if you want to do something with it, right? But for now, this was nothing to save, so I will just leave everything that we have here, and we'll start afresh now with the demo of the 3 different regimes here. And in order to familiarize yourself already with that, I will now use 2D fields. And I think you already saw some 2D fields in Gregor's demo a couple of minutes ago. So the big thing that changes with 3D fields is if you plot them here, so we'll plot this field, you will not have the lines, the 3 different colored lines, but because we are now in 2 dimensions, you will have, instead of these lines, 3 different parts here in the plot. So on the top left side here, you see just the input sum. Here you see just the activation, and here you just see the sigmoided activation. And one thing you should always look for is here the scale. So maybe let me add some input, and it might make some sense. So if I add now a 2D Gaussian input to that, you can see here that the input sum ranges from something like 0, it's like e minus to the factor of minus 31, is almost 0, to 1. While your activation here, even though it looks quite the same, ranges from -5 to -4, right? Because this field again has a resting level of -5. Then here we have no sigmoided activation, so we have no activation above threshold, because that ranges from 0 to 1, and our activation right now is just with -4. So what I want to do now is I want to show you how you can be a bit tricky with Cedar. For example, if we want to now add 3 Gaussian inputs here, I want to create sort of an example scene where there are 3 different items in the scene, and then the field can detect them and select them and also memorize them later. So in order to construct the scene, I will plot sort of the 3 different objects here that we have. And to make this a bit nicer, let me move those around. So let's put the first one here by moving the center variable. That's now also 2-dimensional. Moving each of those centers around. Maybe put this here and put the last one to the bottom, and let's say to the right. And you can see already here in the field we have these 3 different inputs at 3 different locations, and neither of these inputs is above threshold. Now, what we could do in order to manipulate all these 3 things, we could click on each of these Gaussian inputs and manipulate their values. But one thing you want to do in Cedar is, of course, you want to simplify your work as much as possible. And in order to do this, I will show you 2 of the most basic steps in Cedar, which help you in building your architectures in a bit more efficient way. And these would be the sum step and the static gain step. So the sum step does what you think it does. It sums up everything that you put in here. So if I put in these 3 things and plot the sum step, you see I have 3 inputs, 1, 2, 3, and then the sum is, of course, all these things together. And I can then use this output of the sum step to process it using another step. And this would be then the static gain step. And the static gain is nothing but a scalar multiplication, actually. So right now I have this gain factor here that is 1. So if I plot the static gain, I can see input and output. Input is from 0 to 1, and the output is also from 0 to 1. And if I now multiply with something, let's say 8, then everything here will be multiplied by 8. And this helps us a lot, because then we have changed the output of all 3 Gaussian inputs by using only 1 variable, right? So if you want to tune something later and you're not quite sure what the input of all 3 should be, makes sense to use only 1 static gain that you play around with. Then you can choose the output of the static gain here and put it into this neural field. And what happens now is, because this is sort of, and it has an amplitude of 8 for each of these peaks or inputs here, they will all form a peak here in our sigmoided activation field. And you can already see that this only has 1 color, and that's because the sigmoid is so sharp, right? So everything here is 0 and everything here is almost 1. So this is why there's basically only 2 colors here. And here I did already something that I wanted to explain earlier. So for each of these plots, you can click at any location and read out the exact value, right? Here you get a rough overview with the legend, but sometimes you really want to know, okay, how high is activation here? And then you can click on it and it says, okay, this is 0.1312, has a value of 8, right? And this one here has a very small value, for example. So by creating the scenery and then connecting it to this neural field and giving it proper amplitude of 8, I already did the first task. So I have a neural field here that is sort of a multi-peak detection field, right? So you put in all these peaks and they stay around. And the next thing that I want to do now is I want to create a working memory field. The difference here would be in this multi-peak detection field, if I remove one input by, for example, deleting this connection, we can do this by clicking on it and pressing delete. Also, the input will be gone, of course, but also the activation will be gone. And we'll try to keep that around now in our working memory version of that field. So what you can always do to create a new field is, of course, drawing it in. But what is also helpful a lot in Cedar is duplicating steps. So what you can do is click on any step and then press Ctrl-D for duplicate, and we'll create a copy of the field that you duplicated. This helps then, of course, to play around with the parameters, and you don't have to set up everything. So what I will do now is I will connect this thing. I will name it now working memory, because this is what we want to achieve here. And I will also plot this working memory. And right now, because the parameters are the same, you will see also the same result here to the input. So the idea behind the working memory fields now, if you remember it from the lectures, that you have almost no global inhibition, and you have a lot of self-excitation to keep the activation around. So let me show you for demonstrative purposes what happens if we only use excitation here. So first, I remove the global inhibition and choose the parameter to be 0. And then I want to increase the amplitude of our excitatory kernel. So let's say I just scroll up here and increase this more and more. You will see that something very interesting happens, and that is that the activation grows and grows until the whole field here is filled, right? And this is because there's no inhibition anymore in the system. The excitation is very strong. So whenever there's something above threshold, it excites all these nearby areas and itself, and those then excite again their neighboring areas and so on. And so at the end, the whole field is excited. That's, of course, something we want to avoid. And this is where we actually need the Mexican head kernel that I showed you before. So the idea is really we want to excite only a center region, and we don't want it to grow over that center region. So we need sort of this inhibitory ring around that. So what we do in 1D, we can also do in 2D. So we add here another Gaussian kernel, and we want to have a negative amplitude, and we want it to be bigger. And usually a rule of thumb that I use is I just use the sigma twice as large. So let's say -6. Let's maybe not choose -1, but -10. And then we will see already, okay, even though that we have a lot of self-excitation, we still have 3 distinct peaks and not the whole field is covered. Let's see if now the whole thing is also a working memory field. So if we remove here now an input, we'll actually see that it did not help at all, right? So the excitation is not high enough. So in order to get working memory, we really need to increase the excitation even more. This kind of parameter tuning feels a bit random, but it actually, if you follow some heuristics here, you can get to the right parameter values very fast. And depending on the inputs, there's also no easy solution to calculate them. So this is why this tuning manually helps a lot. And this is actually what Cedar enables. So if you want, even if you want to build any project later in code, it's always helpful to find out the parameters while having this visual feedback here. So I did this already before, and let's say we have to ramp up the excitation a lot more, let's say 30 again, and then ramp this also to maybe 28. So we just increase the whole effect, right? We put in way more excitation, but also more global inhibition, so that not everything will explode, and then it should work. But we now achieved another problem that will actually happen to you a lot, is while tuning our parameters, we got some weird artifacts here, right? Because the whole thing was excited, And in order to get rid of those, I want to show this here. You can do this by clicking on the field and then choosing reset, which will reset the field and then only give you activation based on the input. I think the same, the simulator has the same function. If you want to reset your whole architecture, you don't have to click on every field here, but you can use the big reset button that's right next to the play and pause button. So if you click here, also all fields will be resetted. So now we have a really high excitation and a high local inhibition. If I remove now one of the inputs, you will see that it's actually gone in the input. Also in the multi-peak detection field, there's no field anymore, but in our working memory, it actually stays around. You can see here in the activation that it's maybe not as supported as the other two, but it's still above threshold and it keeps itself there. So you could even remove the other three. You can still have 3 peaks here in the working memory field. But of course, now if you reset everything, then you will also lose your memory because there's no input now anymore to form these peaks. So this would be example number 2 of the working memory field. And in order to achieve this, we needed no global inhibition, a lot of self-excitation, and also a similar high amount of global inhibition. So the last thing that I want to do now is create a selective field. And that works quite similar. So this is why I copy it again. I will also do plot again, maybe move this here, give it the same input. And now the idea is a selective field is, if you remember it from the lecture, it has a lot of global inhibition, right? Because wherever one peak is, it should inhibit all other peaks. This makes it selective then. So we need a lot of global inhibition and no local inhibition actually because of that. So first, I will remove here the local inhibition. You can do that by clicking on the X button here. This will remove the entire kernel. Now we have again the problem that everything fills here, but we will change this soon by increasing the global inhibition. And let's say we use something like 0.3. And that is actually a lot, even though here we used parameters like 30. And this is the case because the global inhibition is really applied on all positions here and not only on a single area. And this is why these parameters of the global inhibition always range in this different scale, basically. So what we achieved here, I'm not sure if you can see it on your screens, is we have some global inhibition, but we still have some peaks around, right? So in order for it to really work, we want only one peak in a selective field. We need to increase the global inhibition even more. Let's say 0.4. And this seemed to have worked, but now we want to also increase this effect. So it's, for example, also helpful to increase the self-excitation even more. Let's say something like 40, because then a peak that becomes supra threshold, so above threshold, also has more activation there and then also provides more global inhibition. So by adding sort of more self-excitation here, I virtually increase also the inhibition in the field. And sort of by having now this very high self-excitation of 40 and having this high global inhibition of minus 0.4, I created here a selective field. Let me move that around here so you can see it better. And what now happens if you reset this field is it should form peaks at different locations. So maybe not right now, but yeah, if you click on it long enough, then you also get lucky with the noise here. If you increase the noise of this field, you can of course also increase sort of the change the peaks that will be selected here. And noise is also important if you have 3 inputs that are not exactly the same in order to make the field still selective on all inputs. But that's maybe something that you can find out in your own works. These were sort of the 3 examples for the 3 major regimes. I now used a specific set of values here, but as I said before, you can find really multiple ranges of values to get into these regimes. And I really encourage you to try this out at home, maybe even build these 3 fields on your own. And the idea is then, once you have accomplished this, or at least follow this video, then you can try out your own, trying to build your own first dynamic field architecture. And this would be this architecture here that uses all the fields that we have right now. So the idea is we have a similar scene as before with 3 inputs maybe, and we have here a scene representation that represents just all objects that are there. So we have a multi-peak field that you have seen already. And the trick already that comes in now is basically that we now, instead of putting them all next to one another, like they all get the same input from the scene, we now put them one after another. The idea is that we have here a selective spatial match field where only one peak gets selected, and only the peak that gets selected is then forwarded to working memory. So we build sort of an architecture that memorizes what we did select earlier, right? So that is the idea. And an additional twist that we want to use here is that we don't want to select just any peak, but we also want to give sort of a spatial bias. Here in this case, we want to give sort of an advantage to objects that are located to the left-hand side. And you can do this, for example, by providing a Gaussian input that might be very small, but just gives a slight advantage to the left side. And this slight advantage might then already be enough to always favor peaks on the left-hand side. That's similar to what Gregor just said in his lecture, where he said that like these small differences in input, they have a really a huge effect later on the choice already. So this would be sort of the homework that I encourage you to do. And for that, you need to download Cedar and then follow these instructions here in the text or try it out on your own. And if you have any questions about that, either ask them now or also in the forum. I will monitor that closely. So yeah, if you're interested, ask any questions right now. Otherwise, I will also show you the sample solution tomorrow before the first lecture begins. So at 3 tomorrow, I will show the solutions. Oh, I see. There is something in the chat already. Okay, what I did create, yeah.
Comments from John.
Yeah, okay. Maybe I stop this here so I can see people. Yeah, it seems like there are no questions right now, but I think they will usually come up once you try it out yourself. So don't hesitate to ask us in the forum, or you can also write me via emails, right? I already harassed you with a lot of emails during this summer school, so feel free to return the favor and send me some emails and ask some questions. And otherwise, I will now hand over to Daniel, who will show now the DFF dynamic field flow framework.
Yep. Can you hear me and see my screen? Can you hear me and see my screen? Apparently you can't hear me.
Yeah.
Okay. Yeah. Okay. So I'm trying to keep this very short since we're out of time. So like Professor Schöner said already, dynamic field flow is a text-based programming library for Python. And the idea is that you specify your DFT architecture using Python code. So essentially you do the analogous thing to what you do in Cedar, but in text-based programming. So you define steps, for example, a field, you set parameters to these steps, and you connect the steps with one another. So for example, here's a custom input step, which is then connected to a field. And the advantage of this text-based programming is first that you can run other Python code that does something else, like you can integrate it into some existing Python program, for example, like a connectionist network that generates some activation patterns. And you can then connect such other computed Python arrays to neural fields. And this way you're quite flexible in how you can embed dynamic field architectures into other ecosystems, or the other way around. Second advantage is that you can use variables and loops and things like that. So for example, here we have a loop that is run 100 times and that generates a field in each loop iteration, which would be quite cumbersome to do in a graphical programming environment, where you would have to create each field individually and make sure all the parameters match. Yeah, the next advantage is that we can benefit from existing Python libraries for machine learning, and one of these is called Tensorflow. And Tensorflow works by so what you do is you supply Tensorflow with what's called a computational graph, which is a data structure that specifies how a certain computation should be performed. And that computational graph can then be run by Tensorflow on different kinds of devices, for example, CPU or GPU, or even more specialized hardware, which runs this computational graph in the most efficient way possible. And dynamic field flow is essentially composed of two parts. So it provides a high-level API that allows you to specify dynamic field theory architectures. And the second part is it converts this dynamic field theory architecture into a representation of a computational graph that runs the simulation. And that can then be used to be run in a highly efficient fashion on various hardware. So the advantage of this approach is that, first of all, you have text-based programming, so you can automate tasks, which would be quite cumbersome to do if you had to do things manually. Another advantage, like I said already, is better performance. And here we see a performance comparison. So this is a bit of an unfair comparison because this plots the computation duration as a function of field size. And normally you don't have such big field sizes, but still this gives you an idea of how you can benefit from using a GPU if you have a large architecture and you want to simulate a lot of different things over multiple data and things like that. So what you see here is that up to a field size of 1,000 by 1,000, so that's actually quadratic, you have constant duration for running the simulation in dynamic field flow, but a linear increase in Cedar. A third advantage is that TensorFlow allows automatic optimization of parameters. So this means if you want to optimize some loss function, so you don't want to choose your parameters manually, but rather you want to say, I want a selective field, for example. You could just say define a loss function which characterizes how selective the field is, and then you ask the library to automatically determine a set of parameters that minimizes this loss function. Or you could do other more sophisticated things. So right now we're running a project where we're trying to fit dynamic field architecture to human reaction times, and we wanted to determine the parameters of fields automatically such that the field matches the human data. And finally, like I said already, you can interface dynamic field flow architecture with other Python programs, which could be, for example, programs that programmatically generate some input data to the fields, among which are, for example, deep neural networks. The disadvantages of this is that, unlike Cedar, you don't have a graphical overview over the architecture, and you need Python programming skills. And finally, live tuning is a bit cumbersome, although we're working on that. So live tuning means that you're running the simulation, and as you're doing that, you're making changes to the architecture. So you can find a link to dynamic field flow on the software page on dynamicfieldtheory.org down here, and that will lead you to a Git repository. And to get you started in using dynamic field flow, you take a look at this so-called Jupyter notebook, Getting Started, which essentially is a tutorial in how to install dynamic field flow, how to generate architectures, how to simulate architectures and plot the activation of fields. And then there are a few exercises which are almost identical to the exercises that Jan presented for Cedar. So if you're interested in using this, which I would only recommend to experienced Python programmers, have a look at this. And you can, of course, feel free to ask questions in the forum. And you may also, if you're attending the workshop, I offer that you can do a workshop project of your choosing using dynamic field flow. And given that this is rather new and not as well documented as Cedar or Sabina, I offer you more interactive coaching so that you can really get all the knowledge about the library that's necessary to realize your project.